Alright, thanks for watching, and today I would like to define the most important set in analysis, the Cantor set. And yes, it's not a very endearing term. You can't just say, I love you so much, you're my Cantor. No, it's kind of a Halloween vibe to it. That said, it is very important, so let's construct it, and it's a very nice construction. So step 1, start with the interval 0, 1. So F1 is 0, 1. And then you can split this into 3 pieces, to like 3 numbers, 1/3 and 2/3. And just remove the middle piece. And once you remove it, you get 2 subintervals, and those will be called F2. So step 2. So you have the 2 subintervals, 0, 1/3, and then 2/3. And 1, and then you just get F2, which is 0, 1/3, close interval, union, 2/3 and 1. And then you just continue. Each subpiece, divide them up into 3 pieces, and just remove the middle third of each subpiece. So step 3, you get, I think, 0, 1/9, 2/9, and then 1/3, and then I believe 2/3, which is 6/9 and 7/9, and 8/9 and 1. And that gives you F3. And then just continue in the same way. Namely, given any Fn, you define Fn plus 1 by just removing the middle third of each Fn. So, and then in general, given Fn, define Fn plus 1 by removing the middle third of each subinterval. Of Fn. And then essentially you get this nice hierarchy of sets. So again, we started with F1, and then we had F2, and then we had F3, and then we have F4. So very unstable IKEA set, if you want. And then essentially, essentially then what we want to take is just the intersection. So F, which is called the Cantor set, is the intersection. So definition, so the Cantor set, I love this word, it's just defined to be F, which is the intersection from 1 to infinity of Fn. And the rest of today's video is just stating a couple of neat properties of the Cantor set. Remember, F is just the intersection of all those little pieces. Now, first of all, F is a closed set. And why is that true? Because each Fn is closed. And you're just taking the intersection of infinitely many closed sets. Moreover, and kind of what's more interesting, is that F is non-empty. Because it could be possible that if you take the intersection of those infinitely many sets, that the intersection might be empty. But this is not true because of the video I've done on the finite intersection property. Notice the Fn, they're kind of decreasing and closed and non-empty. So by the finite intersection property, the intersection is non-empty. That's a good application, if you want, of the finite intersection property. Moreover, let's check out the following. So what is the size of F? So let's look at let's say f1, 2, f3, which, remember, it's the thing with 0 and 1/9, right? Well, in that case, f3, how many pieces does it have? So f3 has 4 pieces, which if you want, it's 2 squared, which is 2 to the 3 minus 1 pieces. Of what length? Of length, well, 1/9, which is 1/3 squared, which is 1/3 to the 3 minus 1. And indeed, this is also true for Fn. So, Fn has 2 to the n minus 1 pieces of length 1/3 to the n minus 1. And in particular, the total length of Fn is just this times this. Because each piece times the length of each piece. So number of pieces times the length of each piece. So the length of Fn is, if you want, 2 to the n minus 1 times 1/3 to the n minus 1, which is just 2/3 to the n minus 1. But the point is, as n goes to infinity, this goes to 0. So what is the length of f? Well, it's smaller than the length of any of the fn's, so the length of f is actually 0. So the size, or the length, it's what's called the measure of f, is 0. That said, even though the length is 0, the cool thing is f is uncountable. So kind of you have to picture f as being a huge number of just dust, which has size 0.